All right, so in this exercise, we're going to go over a combination series parallel circuit right here. We're going to go over the rules again real quick, and I'm also accompanied by my colleague Corey. Say hey, Corey.
How you doing, guys?
Uh, so remember, with series circuits, resistance is additive. So if I had one resistor, this is a resistor, and I had no resistor, that's another resistor. The resistance is added between the two. So if this is 1k ohm and this is 1k ohm, I have 2k ohms. Okay. Voltage is additive in the same way that resistors are. So if this is a double A battery, 1.5 volts, and this is a double A battery, 1.5 volts, now I have 3 volts. And current is common. That's going to make a little bit more sense after the exercise. Parallel circuits, the resistance is added with the inverse of the sum of the inverses formula. We're going to go over that more in this exercise. Also, I want you to understand it clearly. It could be the inverse of the sum of the conductances also, depending on how you look at it, and I'm going to try to explain that differently. And voltage is common across the different branches of a parallel circuit, and current is additive using Kirchhoff's law. And you got to remember that means that the amount of current going into a portion of the parallel branch has to be the same amount going out. It has to add up. So let's go ahead and start this exercise. All right, so in this exercise, you see we have 4 resistors, R1, R2, R3, and R4. We need to get the analysis, the calculations for each position in the circuit. You see that we have a parallel circuit here, and then there's a resistor in series with this parallel circuit, and then this entire arm is in parallel with this resistor, and all that's in parallel with the applied voltage of 12 volts. So the first thing we want to do is write down our given amounts, our variables. So our applied voltage is 12 volts. R1, resistance of R1 is 1k ohm. R2 is 3.3k ohms. R3 is 3.9k ohms, and R4 is 6.8k ohm. So now we need to be able to find the total resistance. We also need to find the voltage going across each one and the resistance going through each resistor. So to find the total resistance, we have to break the circuit up into different sections. First, we need to find the resistance of this portion of the circuit, with this parallel portion. So to make those calculations, we need the calculator. Now, remember, we're going to use the inverse of the sum of the inverses formula, and I'm going to go over that a little bit more in depth right now. We have R3 and R4, so we need to get the inverse of R3 plus the inverse of R4. Now, when you inverse a resistance measurement, you get a value that's equal to conductance. Okay. Resistance is measured in ohms, and conductance is measured in mhos. You notice it's ohms, and then mhos is ohm backwards. So it's just a nice way to think about it. Some people measure conductance in a value called Siemens. It's named after the corporation. I like mhos. It makes it easier to remember because it's ohms backwards. So when I take the inverse of R3, which is 3900, 3900 ohms, I get 0.000256 mhos, or 256.4 micromhos. So I'm going to write that down. 0.000256.4, and that's the inverse of R3. Now I need to get the inverse of R4, which would be 1 divided by 6800, and that's 0.000147.1 mhos. I shouldn't have put that point right there. That's my mistake. Just forget that happened. Let me move this paper up a little bit so you can see it. So what we need to do is we need to add these conductive values together and then get the inverse of that number. So on my calculator, I'm going to add the 0.000256.4, and that gives me 403 micromhos. So then I go 1 divided by 0.000403, and it's 458. Just get 6 significant digits. And so that gives me the equivalent resistance of these three. Okay? And so the annotation for that would be R3 parallel 4 equals 2478.6 ohms. All right. Does that make sense, Corey?
Yes, it sure does.
All right. So we can take that value right here, and we can go ahead and fill it into this portion of the chart. Now that we have the equivalent resistance of this portion, we'll add it to this resistance. So we can get the entire resistance of just that branch, just this branch. And that would be 2478.6 ohms plus 3300. So we'll just go ahead and use our calculator and add that. And it's 5778.6 ohms. Okay, so this entire branch added together, because this portion's in series with this entire branch added together is 5778.6 ohms.
Right.
So then we need to put this value in parallel to that value. Okay? And then that will give us our total resistance across the circuit. It's also called the Thevenin equivalent value. So what I'll do is I could do all of this in one line in my calculator, and I'll show you how real quick. We're just going to do 1 divided by 2 cents parentheses, okay? Because we need parentheses around each portion of this, and then we need all of this in parentheses. Okay, so we'll have 2 sets of parentheses. 1 divided by 1000, and that's for that R1 value. Close parentheses plus open parentheses. 1 divided by 5778.6, close parentheses, twice. And that gives us the equivalent resistance for the total circuit of 852.4769. We'll say 0.5. 852.5 ohms. Okay? So then we can easily just get our total current in the circuit. Now, Corey, what's the formula going to be for that?
It's going to be E over I R.
That's
Sorry, E being voltage, I being current, and R being resistance. That's Ohm's law.
right. So the formula to find current would be what?
So you go ahead and you cover up the I, because that's what you're searching for, and you're going to do voltage, which is the E again, divided by the resistance. So the current, the total amount of voltage, which is 12 volts, we divided by the total amount of resistance, which we've already found was 852.5 ohms.
Right. So that means that we have an equivalent or a total current draw of 14.08 milliamps. So I'm going to go ahead and write that down. All right, so that also means that when we add up each current drop across each portion of this circuit, it should all add up to 14.08. And And so we're doing the mathematics separately. We're doing this portion on its own. Then we add up all these separately, and they should equal each other. And we'll see that more in a moment. All right, so now we need to find the current drop and the voltage drop across each resistor. What do you think the voltage drop is going to be for R1, Corey?
All right, so in a parallel circuit, voltage is common, so it would be 12 volts.
Right, it's 12 volts. So we're going to mark that 12 volts. And so now we can go ahead and find the current going across R1. So what would the formula be for that, Corey?
So the formula being that, again, we're looking for current, so we go ahead and divide the voltage by the resistance, which is 12 volts divided by 1 kilo ohm,
or 1,000 ohms, and so that's 12 milliamps.
Right.
All right, so that means also, though, since we're doing this math independent of our current total, but if this is correct and this is correct, which they are, that means his entire arm can't draw more than 2.08 amps for it to add up. So we need to keep that in mind as we're going. If we see that we're going in a different direction, we need to check our work or maybe start over. But that's just the way to check yourself, because that way you don't make a mistake as you go. All right, so now we need to find the current going through R2. Now this might be kind of tricky because you see there's 3 different resistors in this arm. And it is true that voltage is common across this arm. So this across this entire arm, it is 12 volts, but this is going to have a different voltage drop than these.
Right.
But the current going through this resistor will be the same current going through the combination of both of these together. So if, just as an example, if 10 milliamps is flowing through this resistor, when you add these two together, you'll get 10 milliamps at this point of Kirchhoff's law. So let's go ahead and figure out how much current we have going through R2. And we already found that the total for this branch is 5778.6 ohms. So we just need to take that and divide it by the 12 volts being applied across this entire arm. So that would be 12 divided by 5778.6. So that means the entire arm has a voltage drop of 0.00208 amps, or 2.08 milliamps. And if you recall, that's what we needed to equal 14.08 milliamps here. So we're on the right track so far. But if we got a different answer, we would know it was wrong, and we need to go back and check our work. That's where people make mistakes, is they don't check themselves as they go. So the current going through R2 is 2.08 milliamps. And again, that is the value we were expecting. Next, we need to find the voltage going through R2, or being dropped by R2. And to do that, we have the resistive measurement for the calculation, and we also now we have the current going through it. So then we take our calculator, and so what would the formula be to find the voltage being dropped by R2, Corey?
All right, so in order to figure that out, go ahead and cover up that E for me. There we go. So now we're left with I times R, which is going to be, if I remember correctly, that's going to be 2.08 milliamps times the resistor, which is 3.3 kilo ohm. Kilo ohms.
Right. Now to do that, though, remember we have to enter it in decimal notation. So 2.08 milliamps is 0.00208. Okay.
Correct.
You can't just type in 2.08. You will not get the correct answer. And that means that we're getting a voltage drop of 6.86 volts. Everybody see that? All right. So that means that we know the voltage going across these two, because this this whole branch is 12 volts. And if we don't have the 6.86 volts, we're left with, 5.2 roughly. So let's go ahead and get that number, 12 minus 6.86, and we're left with 5.14. So now we know the voltage going across this parallel circuit, and again, voltage is common and parallel, is 5.14 volts. Okay, so then it's just a small step to get the current drop across each resistor at that point. So let's just do that math real quick. That would be voltage divided by resistance. 5.14 divided by 3,900, and that'll be 1.32 milliamps, and then 5.14 divided by 6,800, and that's actually a microamp measurement, but we're going to write it out in milliamp notation. 0.755 milliamps, but you could say 755.9 microamps, and depending on how, if you're in a class, depending on how your instructor is expecting the answer to be, that answer could be fine. So these two numbers, this current measurement and this current measurement, should add up to the current going through R2, which is right here. So let's see if they do. So we add 132 or 1.32 milliamps to it, and we should get 2.08, and we do 2.08 milliamps. So that's another way we can check it, and it's accurate. We can also check this way too, because we know the voltage going across this, and we also have these values right here. So let's go and fill those in. 5.14 volts, 5.14 divided by 2478.6 ohms, which is the total equivalent resistance of this portion, and we should get 2.8 or 08, excuse me, and we do. Does that make sense? Corey, you good?
Yeah, I'm good.
Well, actually, it's 2.07. It doesn't round up to 2.08 in this last example. We're going to write that off as rounding error. This is why I always try to use at least 3 significant digits. I don't usually use more than 6. So, but keep that in mind. This is a good example of a rounding error happening. And that could be a very big deal, especially if you're in a school or if you have a precision project where you don't have much tolerance. You want to have more significant digits. Do you have any questions, Corey?
No, I'm good.
Did you have anything you wanted to note, or anything that you see that was interesting or unusual that you weren't expecting?
I did want to note for the audience that it's always good to go ahead and break down these circuits, even though this one's not really as complex as you might see out in the field or out, even a school situation or environment. That it's still always good to break these down, like how we did between resistor 1 back to the power supply, the 12 volts, and then from resistor 1 over on to the other last 3 resistors. It makes it a lot easier to break it down like that instead of trying to tackle it all in one piece.
Also, I like to point out that this is an interview question. So, like, if you were applying for a job or you're expected to work on a bench or do this kind of work professionally, this is the kind of stuff they would ask you on an interview question, on a test. And this is advanced for that. They might ask you questions about capacitive reactance and filters and stuff like that also, and we'll cover that in a later video. But just keep that in mind. If you have trouble with this, you're going to have trouble in the real world working in this profession.
Right. And this is also questions that you'll see on a lot of certifiable exams, such as your CAT training.
Right. And the certified electronic technician exam, you have to know this kind of stuff. So and you can't really go any further in your electronic theory knowledge if you don't understand this very clear.
Right.
So if you have any questions, leave them in the comments, and have a good night.